Okay, we've done a calorimetry experiment, but I wanted to make sure we are good to go on our notes when it comes to the calculations, because you will do this on the exam. So we have discussed about the specific heat. Now remember, lots of good notes about here, but the specific heat is the amount of energy required to raise the temperature 1 gram of to raise the temperature of 1 gram of substance by 1 degree Celsius or 1 Kelvin. It's the same increment. And then we use this equation, that is the MCAT equation, that's mass times specific heat times the delta T. The reason why that P is there is, as you'll note here, it's at constant pressure. So that P is just there as a reminder to the reader that it's at constant pressure. So example number 1 says a 32.0 gram sample of copper was heated from 16.0 degrees Celsius to 61.0 degrees Celsius when it absorbed 554 joules of heat. Calculate the specific heat of copper. So we will use that Q equals MCAT equation. Now let's check out our delta T first. That would be our final minus our initial, right? T final minus T initial. So that would be 61.0 minus 16.0, keeping 1 decimal place, and that is going to be 45 degrees Celsius. And so we now know Q, that's Q, and then this is our mass. So for 554 joules is equal to 32.0 grams times that specific heat, we'll call it C, and delta T is 45 degrees Celsius. Okay, so what we'll have to do is divide both sides by 32.0 and 45, and 32.0 times 45, and those go away, that goes away, and so 554 divided by 32 divided by 45, and is going to be, so I know I'm running out of space, 0.38, let's keep 3 sig figs, so 385 joules per grams degrees Celsius. Okay, so pretty simple. That one's pretty straightforward. Now let's see if we can get a better pen in here. And let's do example number 2. So the specific heat of aluminum is 0.899. If a 75 gram sample of aluminum is heated for 20, how much heat in joules did the sample of aluminum gain? So here's our delta T. Let's go ahead and calculate that. Delta T is 40 minus 25, so that should be 15.0 degrees Celsius. So that's pretty easy. Q equals MCAT again. So Q equals your mass, which is 75.0, times your specific heat, which is 0.899, and your delta T is going to be 15.0 this time. So 75 times 0.899 is going to give you 1,011, but we want to keep 3 sig figs, so we're going to go 1,010 in joules. Good. Now example 8, what would be the temperature of a 24.2 gram sample of carbon if 575.6 joules of energy was applied to a sample originally at 25 degrees Celsius? So that is the initial temperature. I want to know the final temperature, right? That's the one I want to know. Now what's the specific heat? That's a good question. Well, since we're with carbon, remember specific heat is specific to that element or that substance. So there's carbon, so that means we're going to use that guy. The specific heat is 0.709. joules per grams degrees Celsius. So that means that we'll do that same Q equals MCAT equation. The Q is 575.6 joules. That's this guy. And that equals our mass, 24.2 grams, times our specific heat, 0.709 joules per grams degrees Celsius. And then our delta T is actually going to be T final minus T initial, right? So we don't know the final, but we do know the initial, so that's 25. Okay. So I'm going to cut out units from now on to get rid of that. So we have that TF, but the minus 25 is kind of in there. So we can't just divide by 25. That's not going to work. So math is going to allow us to divide by 24.2 and 0.709 and get these guys out of here. And we'll get 24.2 and 0.709. And so 5.6. And so that gives us 33.5. I'm going to write a bunch of decimals just so we don't get as much rounding error. So that's T final minus 25 now. Okay, that's what we're left with. So to get rid of that 25 now, we'll just add 25, and we'll add 25 as well to here. And so our T final, we ran out of room, so we have to go over here. And we'll add 25, and that will be 58.55, but we should actually round it to 2 sig figs, looks like. So we'll just call it 59 degrees Celsius. Okay? Simple enough. For example 4, a sample of water raised its temperature from 45.7 degrees Celsius to 89.9 degrees Celsius when 4.36 kilojoules. Oh, well, I bet you we'll have to get rid of that. 4.36 kilojoules. Let's change kilojoules into joules. There's 1,000 joules per kilojoule. So that's going to be 4360 joules. Okay? So I'm moving the decimal place over 3 places to the right. That's that trick. So what is the mass? So I want to know the mass. I now know the initial and the final temperature. I know the heat. And it's water, so I know its specific heat. Now the specific heat of water is 4.18 joules per grams degrees Celsius. You can find that on the table, but you should also memorize that one because it comes up a lot. So yeah, we should be able to work this out easy. Q equals MCAT. Q is 4360, and then the mass is unknown. Specific heat is 4.18, and the change in temperature is, let's see, what's our delta T? 89.9 minus 45.7 is 44.2. So that's 44.2. And so the mass is going to be, because I won't write out the derivation of it. You guys should know some math. So there's 23.2 This should be grams. All right. So I hope that helps. Now we're going to do calorimetry. So the process of heating it up, I thought I had more calorimetry problems. So we need to make sure we understand the whole calorimeter thing. You need to be able to draw a calorimeter and understand that you're heating up. You heat up a piece of metal, right? And then you place it into cool water. So this thing is very hot, right? And all those hot particles are moving around really quickly, and then they end up touching the slower moving particles here, because this is room temperature water, and it heats up the water, right? And it heats it up until they come to the same temperature. So the temperature of the water will increase so you measure the initial temperature and the final temperature, right? So there you can find the delta T. You can measure the mass of the metal. And if you know the initial temperature of the metal, because you're heating it in a Bunsen burner, right? Let's use a Bunsen burner. You're heating it up here. If you can somehow measure the temperature of that metal, you can know the initial temperature here of the metal. And then the final temperature of the metal is going to be the same as the final temperature of the water, because they're going to equilibrate, right? So then you can find out all sorts of good stuff. You can find out the mass of this metal, and you can also find out the mass of the water in the calorimeter. So you have two different things you're juggling, two different systems, but their heats are going to be the same, which is going to be great. What you find out is that the heat of the metal is lost, so that's why it's negative, and it equals the heat of the water, okay? And that one is gained, so that's why it's positive. So you can rewrite these as negative MCAT and a positive MCAT. So M is for the metal, C is for the metal, specific heat of the metal, and delta T is for the metal. And then the M over here is for the water. This is the C of the water, and this is the delta T of the water, okay? So knowing all these different numbers, you get a bunch of different numbers, but you just have to find the one that you don't know, okay? So here we go. Let's try it. So example number 5, a sample of iron is having a mass of 93.3 grams is heated to 65.58 degrees Celsius, is placed in a 75.0 gram sample of water, raising the temperature from 16.95 degrees Celsius to 22.24 degrees Celsius. Find the specific heat capacity for this iron sample. Okay, so one other extra thing you might want to know is the specific heat of water is 4.18 joules per gram degrees Celsius. And that should be good to go for what we need to know. So again, let's try that. Negative MCAT equals MCAT. That's the kind of method you should think. So this is the sample of, and this is going to be your metal. This side is going to be our metal side. This is going to be our water side. So the metal side is 93.3 grams. So negative 93.3. I'm going to drop units because they're cumbersome. We want to know the specific heat of the iron. So that's our unknown number. Now the change in temperature is going to be a little interesting. it was heated to here. So that's the initial temperature of the iron. Now the final temperature is actually going to be the same as the final temperature of the water. Okay? So the final temperature is going to be 22.24. That's usually where people mess up. 22.24 minus our initial temperature is 65.58. All right. And now let's do the water side. The water is 75.0 grams. We already said the specific heat of water is 4.18. And the change in temperature from this is given to us as 22.24 minus 16.95. So you can simplify this greatly. Let's crunch down our delta T's to make things a little easier. So we'll do okay. So that is simplified a little bit. And what I should have done is I should have simplified the whole thing on this right side. But that's okay. We can do that right now. 75 times 4.18 times 5.29. So that's going to be, you can condense them down if you want. This negative times the negative is going to make that positive. So 93.3 times 43.34 is going to make 4,043.622, and then with the x on there. Okay, so then you'll divide both sides and simplify that and get x by itself. Now you didn't have to condense all these numbers. You could have kept the terms and just done this and then divided by this and then divided by this, and that will work. However you choose to do the math is fine, but you must show your work, please. 1658.415 divided by 4043.622. And so x is going to be 0.410. Looks like 3 sig figs, yeah. And then our units is joules per grams degrees Celsius. So let's check our answer. For iron, iron should be 0.449. Okay. And so this iron sample is 0.410. Why is this one a little lower? Well, it could be systematic error. That would be an error inside of the experiment, maybe misreading or heat loss to the surroundings, because the calorimeter will absorb heat. Or you could have an impure sample. So that's why yours may be a little bit different than the other value, but hopefully that makes sense and that works. All right, have a great day.